I guess I'm supposed to mine the next block now. So this is Josef Widder, who is an associate professor at TUY and also works at Interchain. And he will be talking about basically the Tendermint consensus protocol.
Hello. So I will talk about Tendermint. So I'm here for the Interchain Foundation, and actually we are going to, it's a transition phase soon. The research and development will be called Informal Systems. We're going to spin out, but for now it's Interchain Foundation. I want to introduce a little bit what we are doing and who we are. So two researchers currently accept me to work with me is Igor Konov, who's an expert in all computer verification, and Žarko Milošević, who is expert in distributed algorithms and fault tolerance. And so we are a Swiss non-profit foundation, and we support research and development of secure and scalable decentralized applications. And currently we are focusing, and this is why I'm here, on Cosmos Network and Tendermint. And the question, of course, what does this word mean? So let's start with Cosmos. So Cosmos is our vision of decentralized networks of independent blockchains. So we don't believe that there should be just survivor in these competitions of blockchain and then everyone should run their business on that. Our view is that every community should have their own blockchain and they should live in the Cosmos ecosystem. And they should communicate with each other via inter-blockchain communication protocol. So it's a little bit like villages, cities, and countries. So each blockchain is like a city, and most of the business goes within the city. And sometimes you have to communicate with another city, and then sort of this goes via this inter-blockchain communication protocol. And so as I said, what is said here, that should be like Tendermint. By this we mean that basically we do state machine replication in the classic sense, in Byzantine fault tolerance. So it's a strong finality. This is also the sort of the assumption that lies behind IBC. So Tendermint is this consensus algorithm that is the core of the system. It is Byzantine fault tolerant state machine replication, and it's a modern implementation of classic ideas. Here it says PBFT and TLS. So we say PBFT because more people know it, but the algorithm is closer to the Dworkin-Stockmeier consensus algorithm. And if you know the paper, and you should definitely read the paper, it's the authenticated Byzantine case. And this algorithm is basically the blueprint for what we are doing. I say it's modern because it's designed to run on a wide area network with big numbers of nodes, which requires us that the communication has to be gossip-based in order to be efficient. And everything is open source. You can find all the code online, and which is something which is sometimes embarrassing to me is that actually also our technical discussions are online. So we have the development sessions every week. They are recorded and they are put on YouTube, and then you can see how we say crazy stuff sometimes. So it's you can follow all our discussions there and all our developments. And since this is here a consensus seminar, I have to have one slide on consensus, and that is it. So this is sort of the idea of Tendermint consensus, and this is also why I said it's closer to TLS, because here you don't have sort of this notion of few change and then broadcast. So what you have so someone, the leader proposes a value, then it's checked for validity, then it's pre-voted, then we wait for pre-votes. Then depending on how many pre-votes we get, you have pre-commits, and then depending on what's happened, either if the consensus is not successful, we go to a new round, which means we're going to pick a new leader, or we're going to commit, which means we have generated a new block, and we go to the next height and do this again. That we have this notion of rotating coordinator is sort of part of our idea to fairness. So we want that everyone who participates in the protocol has the chance to actively propose the values and has influence on what is going to happen. And therefore, we have these rotating coordinators, which is weighted over the voting powers. And actually, the system is much more complicated than typical figures that we see, for processes. This is a sketch of how the different roles that we have in Tendermint. So what we have validators. So validators are the nodes typically you see in consensus algorithm that actually participate, that generate new messages, that sign values. And basically all other nodes here are full nodes. They participate in the gossiping, and they also sort of follow the state machine. So they receive the messages. When they have received 2/3 of certain messages, they do the state transition. But if they are not validators, they're not going to generate messages in the sense that they don't sign messages. The reason why we have here these validators here sort of hidden behind the sentry nodes is because at the end of the day it's super complicated to be a validator, because what you need to have your private key on a computer that is online, and it's sort of therefore attackable. And sort of one of the ideas is that the validators actually are not talking directly to the outside world, but they hide behind these sentry nodes. Also, it's not the IP addresses that are known to the protocols. It's just the public keys. So this is part of the security setup that we have. And the client can then talk to sentry nodes. And then from an architecture viewpoint, the important feature of Tendermint is that we have this application blockchain interface. So our view is that every application should run their own blockchain in the idea of being decentralized. But then, of course, when I say every application, I have a very vague view of application in the sense that also a virtual machine can be an application. And actually, there are several projects that implement different virtual machines on top of Tendermint. So there's a virtual machine for Ethereum, for Move, for Pact, for Bosom. I keep forgetting one. I think Agoric. So there has one. So we are open. There are many projects that build on top of Tendermint. And that's sort of to conclude this overview of the past. I want to give the historical background. So Jake Won wrote the white paper Consensus Without Mining to have this idea about proof of stake. And then Ethan Buckman in his master thesis worked on this Tendermint consensus algorithm. Then the idea of the Cosmos network comes from this 2016 white paper. And then in 2018, Žarko Milošević contributed to this. He found some LiveNet sparks in the thesis by Ethan, and so they fixed them here in this archive. That's sort of the historical background of the Tendermint project. Mr. White, do you have questions? Then I go on. So, to give some idea what we are currently doing, and one of the projects that we are working on right now is the Light client, which is a very modern term. Actually, what in old 90s language, it's basically a read. So we have here this view of the Tendermint blockchain, where you have here these nodes that run the application, and we want to have that clients from time to time connect and want to check a block. And it should be light in the sense that they should not be forced to do all the computations. If they sleep for a day and come back, we do not want, if they just want to see the most recent block, we don't want them that they have to follow all the blocks that have been generated. That's the problem. So the security model that lies behind in our solution is every validator has some voting power. the validator set can potentially change at the end of every block. So in the consensus, the validators also decide who is going to be the validators for the next consensus instance. But this validator set change is controlled by the application, which also means it can totally change. There are no assumptions on this change in the consensus middleware. And because we have this proof of stake, and if you want to get the stake out, you have to wait some time in order that we can check whether you behaved nicely. We have this assumption that if a block is committed at time t, then the set of the next validators, 2/3 of them must be correct until t plus tp. So tp is this trusting period, which is imposed by the unbonding period. It's a little bit complicated. Let's see a figure. So assume here we have here the time axis t. At this time instance here, we have a block generated. Here is a depiction of the validator set. There might be some faulty ones here, and there are some correct ones here. And the assumption is that during this trusting period, these guys in here behave correctly, and that most these guys here behave faulty. And if at some later point in time, another block is generated, and a new validator set is elected, then it might look like this. So you have here some correct guys again, some faulty guys, and in this, for this trusting period, this holds. This also somehow means that when we have these overlappings here, and they are typically very long, because blocks are generated every 5 to 6 seconds, and this trusting period in the current blockchain is 3 weeks. When we have this overlapping, this generates restrictions about who can be correct and who can be faulty. Now, of course, the problem now that the light client faces is the following. So, for example, I don't know, a block was generated, I don't know, at this point here, and then it goes to sleep for a week. It comes here. It has a new validator set. It gets a block with the validator set. Can it trust this new block or not? And that's the problem that we have. So in principle, what is quite easy to observe, so if, for example, the light client sees this block here, it goes to sleep and wakes up here, there's no trust it has left. The last information it had was this one. This information is outdated and it cannot do anything. So at this point, the only thing you can do is you go to your favorite newspaper dealer and ask him, can you give me a new trusted header that I can use to get new states? But if the light client is online every other day, or say once every week, we want to ensure that with the trust that it has, by knowing that this header here was correctly generated, that it can verify this header, possibly without checking too many headers here in between. And that's the problem we are looking at. So the problem is you have to track validator changes. As I said, it's a read, but we cannot do the classic read that you could do when you had a static membership in state machine replication. In the old days, you ask just everyone who participates, give me the current state. You wait until you receive f+1 identical answers. You know one correct guy was among them, and you're happy. Now you don't even know who to ask, because the validator set can change all the time. So the security of this light client depends on the proof of stake timing assumption, as I said. So we have to use this time in order to establish the trust. And of course, that eventually, so this is not the security, but the liveness, eventually actually we can connect to a correct node to give us blocks. So how does it work? Well, the light client is initialized with the trusted header H1, which is sort of the root for its trust. It downloads this new header it's interested in verifying, and it tries to verify the new header based on information that is in H1 and the age of this block. And then, once it has verified the new header H2, it has enough information to to extract all the information from the application as Merkle proof. So here's just one sketch, one part of the header verification, just to give you an idea of what we are doing. So that function here has an old header, H1, which is trusted, and a new header H2. First, we check that the old header isn't expired. If the old header expired, we have to say we cannot give you any trust on H2. Then we compute the voting power that was there in the old header. Then here we check that the header H2 is correctly signed. So this is just the condition about the well-formedness of the header H2. And then this here is the interesting check. Here we check basically that the new header H2 is signed by at least one process that is correct, that we can be sure to be correct by the trusting period assumption. So here we have this 1/3. So intuitively, if sort of the intersection in the validators ensures that 1/3, more than 1/3 of the old validators are still around, then we can do this check. Okay. If this check fails, it doesn't mean that this header here is forged. It might just be the case that between H1 and H2, too many changes in the validator set happen. What we don't have to do, we do some bisecting. So we ask for some header in between in order to generate this trust eventually. So that's what we're currently doing. And actually, I haven't talked at all about the title of the talk, which was about strengthening distributed systems. And I want to talk a little bit about actually the main project that I'm involved in. And this is called, we want to do verification-driven design. So I come from academia, and there we have this ivory tower idea how systems are designed, right? We have an algorithmic idea. We're going to write them in a domain-specific language. We can actually then do some automated verification even on that if you're happy, right? Then from this, we can synthesize the code nicely, automatically, to automate verification, and we get a system. And correct by construction, everything works fine.
Who has that idea?
I am a scientist, yeah. But of course, it's all wrong, no? So we don't have this language. We have pseudocode at best. We have many computational models. We have heard words like weak synchrony, eventual synchrony, partial synchrony. All this is not there are notions in English at best. We don't have formal semantics of that. And on the other side, on the verification side, everything is complicated. We have unbounded state spaces. We have parameters. We have faults. So at the end, we're going to have bugs. And this system and this problem is real. There are bugs in systems, even if peer-reviewed papers. We understand that things happen. So there are some codes. One thing quite hard to follow in the slides, and then we have some bug in the system here, or some small omission in formal specification, and at some point you don't actually have leader election. So this problem is both, of course, on the application side and on the implementation side. And what we try to do is we want to eliminate that. We want to have a more rigorous approach to engineering of systems. So first point, we're going to start with POTSI-style specs, I like to say. So with problem statement assumptions, some solutions, and some arguments why they are correct. And the important point from here is that these specifications, they should be acceptable both for us on the verification side, on the academic side, and for the engineers. If you look at specifications that are written by engineers, they talk about data structures, they talk about APIs, but you will not find a liveness specification of the thing in there, for example. Okay? So you need something to sort of span these both worlds. Then what we want to do, we want to write formal specifications in TLL+. This sort of should make the English formal, and if the English is not formal enough, fix the English at some point. We're going to implementation of these protocols in Rust, and as first step toward correctness, we're going to test the implementation against the TLA specs and vice versa. And finally, we're going to do automated verification of the TLA specs. And I insist on the fact we want to do automated verification. We don't want to spend 5 people, 6 months in writing machine checkable proofs. This is not going to scale in our world where the protocols are changing all the time. We want methods that have a bigger degree of automation. And actually, the light client that I just presented is sort of our first pilot project where we're doing that. And just to convince you that I'm not totally crazy about what I'm claiming here, I want to give you some recent results ahead on automated verification, which I think we made some nice progress. So the first result, I want to talk is verification of protocols. And what we developed in the last, together with Igor, you saw his pictures on the second slide, is the Byzantine model checker. So the problem that we tackled on the high level is parameterized model checking. So when I was in undergrad, model checking meant I would write my protocol for some model checker, fix the parameter n, and do exhaustive state space exploration, and then it would give me counterexamples or not. But then if I would write a paper for Disco-Pozzi, I would write proofs for n, right, which is an arbitrary big n. So what we want to do is in parameterized verification, we want to have a description of the system, check against temporal formulas, but keep n as a parameter. We don't want to fix it. And the algorithms we looked at are very close to the algorithms we have discussed here the last week. Here is a standard example, variable broadcast by Schrickert and Tuek. What you find here is threshold guards. That's the major point. This is also, we have discussed quorums and all that. This is sort of the code representation, how to check whether quorums intersect. And you have these resilience conditions on the system. And what this then gives you, actually, in parameterized verification, is that you have a system of n processes. There's an assumption about the number of faults, and f are actually fault in a run. And you want to check whether for all values n, t, and f that satisfies, for example, this famous n is greater than 3t, that the parallel composition of n minus f correct processes, and these processes are also parameterized because n and t showed up in the code, with f faults, satisfies our safety and liveness properties. And in general, these problems are undecidable. But what we could do is we could, for these threshold-guarded algorithms, define automata for which we actually have nice results. And we can automatically, for the parametric case, check a number of distributed algorithms from the literature. And last week, at the Friede workshop at DISC, Vincent Camoli presented his own work. He's our first user. And he used the Byzantine model checker to check the broadcast of the Red Belly blockchain. So that's quite exciting. And sort of the theoretical underpinning behind, just to give you sort of the idea, we use bounded model checking, which basically means what we can do. We can check execution of a fixed finite length against the specification. But of course, what we want to do is we want to check all executions. And the big question is whether there is an if and only if between them. Actually, what we have done in the last years, we have shown that for these threshold-guided algorithms, we can make this bounded model checking complete for safety and liveness. So that's sort of on the protocol side. Towards the verification of implementation and of code, I've worked together with Cesare Dragoi from INRIA Paris. And what we did here, we digged up some old literature. And sorry, Eli, I call the work communication closure, but there is also a very nice paper by Eli where he calls the concept stratified decomposition. So what's the idea of communication closure? Communication closure basically means is that we have programs that locally go through a sequence of blocks of the code. And for example, the second block of this process here only communicates with the second block of this here. So if they're structured in a way that one block only communicates with the same block of another process, this is a communication closed. Here, the first block sends a message to the second block. This is not communication closed. So we use these notions, and if you think back about also some algorithms we have talked about this week, for example, view change. Typically, you have a lead election phase and you have a broadcast phase. And the lead election messages are not going to interfere with the broadcast, and the broadcasts are not going to interfere with the lead election. Okay, so here you have a decomposition of these algorithms, and they're not interfering. But of course, there's also always a trivial decomposition, right? You can always say the whole program is one layer and everything is fine. The question is which is a good layer of decomposition, and the nicest layer is, of course, if you have message chain 1, which corresponds, in our nice view of distributed computing, to the notion of a round. And if you have notions of the round from a verification viewpoint, it's super exciting, right? You just you don't have interleavings. You don't have to deal with facts like who does the first step or something. You just talk about what messages are sent in a round, which messages are received in a round, which also means you don't have to think about message buffers. If you want to reason about asynchronous system and they do this in an asynchronous environment, so that you have always to carry around invariants about all the message buffers, this you don't have to do in this case. You can reason about the rounds in isolation and you get much simpler proof arguments. So what we've done in that work, we asked two questions: which protocols are communication closed, and how can we compute round decomposition? So we have found an automatic method where we annotate the code that can identify automatically communication closed asynchronous protocols. Once we have them, we're going to rewrite them automatically into synchronous protocols and then do specification on the synchronous protocols. So some idea here. So here you have some schema of this algorithm I've shown you before. And then you sort of have to understand where in the code run the round boundaries. And then you're doing this writing in the synchronous code. Once you have a synchronous code, and of course you prove that the semantics are the same, so they produce indistinguishable executions. And once you have done that, you can pick one of the verification methods for synchronous algorithms that have been developed in the last years, and there's huge interest in the verification community for distributed algorithms. So what we have done, we have taken some algorithms, encoded them in C basically, and these are the invariants, and this gives you the synchronous codes. So we have written them and did also verification, and we used the deductive verification in psync. So to not keep you away much longer from lunch, I talked to you a little bit about what is our idea about Cosmos and Tendermint, what we are currently doing for the light client. And for me, the interesting thing is that what we want to do in the next month is really to sort of re-implement a Tendermint in Rust and do this in a way that we have better trust in the correctness of the systems and the correctness of the protocols. That's all. Thanks.
There's a lot of work going now about this in Hansinger Group. They have a language how to write things round by round, and Muli Sagiv has this EPR system, ERP system proof. And they claim that they don't have a proof yet that everything that can be written round by round can be translated to the EPA, to the ERP or VPR. I don't know
Okay.
what's the order there. And then they have an automated proof to it once you put it in this logic. So I wonder if this doesn't. I expected EPR to come somewhere here, but it didn't.
It's not, yeah, because it's a little bit a different approach still. I didn't know that they work on rewriting into synchronous rounds. So about the work by the Hansinger group, so Cesare actually was in that group. And last week we had a workshop, as I said, in Budapest, and there was also a talk by the Hansinger group that worked on that. And this rewriting into synchronous rounds is currently a hot topic, and there are several groups doing that. At the end, the problem to reason about distributed systems is to handle partial orders, because this is what's going on. And instead of reasoning about sort of all the executions, you just want to pick one execution which represents a possibly big set of executions in the same partial order, and this is what's going on.
This was in '87. Now we know things that this distributed should be round by round.
This is the point that with the idea of stratified decomposition, we sort of say, okay, the moment this is actually the algorithm is in rounds semantically, we can understand how to do that. And while this was in '87 a good idea to write mathematical proofs, and it's a very nice idea, what we try to do is we want to use it for automated reasoning, and this is more recent. This is going on right now.
Okay, well, I guess let's thank the speaker, and maybe we can take the rest of the questions offline. We can have, so people can go to lunch.